December 1942. The North African Desert. A line of American M for Sherman tanks stands motionless near Tebessa, western Tunisia. The sun burns through a thin haze of dust. Heat ripples across the sand, distorting the shape of each vehicle. Their olive-drab paint, clean when shipped from Norfolk 6 weeks earlier, has turned the color of the surrounding earth. The engines idle unevenly. The sound falters, then stops. A crewman opens the engine hatch. A cloud of fine dust escapes, hanging motionless in the still air. The mechanic inside coughs, then signals for tools. The General Motors radial engine beneath him is caked with tan powder. Every surface, filters, manifolds, carburetor throats, is coated. Within minutes of inspection, he finds what the logbook already suspects: air filters completely choked. The machine cannot breathe. At the Ordnance Park nearby, other Shermans show the same condition. Out of 12 tanks, only 5 can start reliably. One has burned out its cylinders entirely. The maintenance sheets list dust ingestion, critical. Supply officers note the rate of failure, 1 in 4 within the first week of operation. Each tank had arrived new from the States, sealed and inspected. Yet here, on open ground, the desert is stripping their engines bare. The official U.S. Army report, filed later that month, describes the environment as mechanically hostile beyond expectation. Airborne sand reaches densities of 0.5 gram per cubic meter during vehicle movement. Standard oil bath filters, designed for temperate conditions, cannot separate particles that fine. The desert dust passes through, scores pistons, and settles in bearings. Once inside, it acts like grinding compound. Technicians set up inspection lines under canvas shades. They clean filters, change oil, reassemble engines. Within hours, the problem returns. The mechanical chain of failure is absolute. The desert air enters, dust circulates, lubrication fails, and the engine dies. No amount of maintenance can outrun the sand. In a nearby tent, a single note is pinned to a report board. Written in pencil by an anonymous crewman, it reads: "We don't need more filters. We need to keep the air out of the filters." No name, no rank. Only frustration turned into a problem statement. By dusk, the maintenance yard falls quiet. The last engine has been shut down to conserve fuel. The horizon glows faintly over the Atlas foothills. In the stillness, a few mechanics remain under dim lantern light, removing filter housings with wrenches and spare parts borrowed from other vehicles. One of them, a corporal from the 2nd Armored Division, studies the way air enters through the top grille. He marks the dust trails with a finger, then wipes it on his sleeve. The sand is fine as flour. It passes through every screen. He doesn't speak. He just looks at the intake once more and mutters to himself, "Stupid design." No one records his name that evening. But within weeks, a crude modification traced back to this very line of tanks would begin circulating across the desert, an idea so simple it was dismissed at first as mechanical nonsense. Early January 1943. The front near Gafsa is quiet. Between patrols, the maintenance area fills with half-repaired vehicles. Mechanics work with minimal shade, surrounded by rows of dismantled air cleaners. Oil pans sit open to the sun. The smell of burnt lubricant mixes with dust and solvent. A corporal named Harlan McCoy, 2nd Armored Division, walks the line carrying a length of canvas hose. He has been assigned to salvage filtration assemblies, non-functional. He removes one from a damaged Sherman and tips it over a tray. A stream of base powder flows out, nearly a quart of it. The filter mesh, clogged solid, weighs almost twice its original mass. Nearby, Sergeant Earl Johnston, his section chief, keeps count with a clipboard. Out of 22 filters inspected, 19 are blocked. 3 have collapsed screens. McCoy records the time to failure, roughly 8 hours of engine use in open desert before restriction becomes critical. He notes that each tank must carry extra oil just to maintain viscosity against dust contamination. At midday, ordnance officers from the U.S. Army's 17th Maintenance Battalion visit the site. They carry a field test rig, essentially a blower fan and collection jars. When the fan runs, they watch how dust flows into the intake. Within seconds, the glass jar turns opaque. One officer remarks that the air in this valley has more dirt than oxygen. Another quietly measures the pressure differential. The reading confirms total airflow loss under combat speed. McCoy examines the filter assembly again. The unit is meant to draw air from the rear deck, through twin inlets lined with mesh, down into an oil bath where particles should settle. But the North African dust is too fine. It floats over the oil surface, passes the baffles, and reaches the carburetors intact. Under magnification, improvised using a magnifying lens from a gun sight, McCoy sees what looks like talcum powder coating the inside wall. That night, he sketches an idea on the back of a maintenance form, a cloth pre-filter tied around the intake mouth. His note reads, "Stops larger grit before the main element." Maybe unnecessary, but worth a try. He cuts strips from a spare tent canvas, wets them in used oil, and wraps them around the grill. To keep them in place, he uses scrap wire from a disassembled radio. The next morning, they run the tank engine for 30 minutes under full throttle. The pressure gauge shows a modest airflow loss but stable operation. When McCoy removes the cloth, it's coated thick with sand, the inner filter remains clear. The sergeant calls it a stupid idea that might actually work. According to later ordnance records, this was the first recorded instance of a field-made external barrier filter on the M4 series in North Africa. No official report names the originator, but crew logs from the same battalion list McCoy mod beside maintenance entries dated January 12, 1943. As word spreads, other crews begin copying the trick using gun cleaning patches, burlap, or even women's stockings sent from home. Each variation looks different, but the purpose is the same, to trap dust before it reaches the intake. Officers hesitate to approve it officially. They call it unscientific, temporary, untested. Yet tanks fitted with the modification last twice as long between overhauls. By the end of the month, that stupid shortcut has reached supply depots at Tibessa, Kasserine, and Spatler. The idea is no longer a rumor, it's a visible field pattern. Trucks leaving for the front show makeshift cloth sleeves flapping behind their engine grills. The desert wind now moves through layers of fabric before reaching steel. In every maintenance log, a quiet observation repeats, engine hours increasing, dust wear decreasing. No one has solved the desert yet, but for the first time, the machines are breathing again. By February 1943, the numbers began to speak louder than any officer's opinion. Maintenance logs arriving at the North African Ordnance Headquarters revealed an unmistakable pattern. Tanks fitted with the improvised pre-filters were surviving the desert. Engine replacements had dropped by more than half. Oil consumption, once alarmingly high, stabilized. Mechanics noted fewer cases of piston scoring, and carburetors remained visibly cleaner even after long convoy runs. The reports arrived from multiple units, each written in different handwriting, yet describing the same phenomenon. Somewhere between makeshift improvisation and field necessity, a consistent solution had appeared. At first, it was dismissed as coincidence. Then the data kept arriving. Crews running unmodified Shermans continued to lose power after every sandstorm. Those with the cloth-wrapped intakes kept moving. At an ordnance depot near Constantine, a group of engineers set up controlled tests using captured desert soil. 2 Shermans were parked side by side beneath a canvas shelter. One remained factory standard, the other carried the now familiar cloth sleeve over its intake. A powerful blower was used to simulate the sand-laden air of a moving column. After 1 hour, the results were plain to see. The standard intake was coated in pale dust. The modified tank remained clean enough for immediate operation. The figures recorded that afternoon would later circulate through official channels. The modified unit had emitted less than a quarter of the dust volume that entered the standard filter. It was a simple, measurable fact, something that could no longer be ignored. The officer in charge, Lieutenant Colonel Frank Balcombe, summarized the observation in his field book with a single sentence: "Field expedient effective beyond expectation." Washington received the data weeks later, stripped of emotion but rich in numbers. Charts showed rising engine reliability, reduced maintenance hours, and lower fuel waste. The evidence was irrefutable. The so-called stupid shortcut had outperformed official equipment in the harshest conditions of the war. In Tunisia, mechanics continued refining the method on their own. Some used treated canvas, others layered oiled burlap or muslin, testing which caught the finest grains. The process was crude, repetitive, and constant: fabric washed, dried, soaked in oil, replaced after each mission. Yet every crew that adopted it found the same result. The engine noise changed from strain to steady. The tanks, once choking in sand, now moved with new confidence across the open flats. When an ordnance inspector visited the front that month, he recorded his impressions in measured prose. Majority of operational tanks employ unofficial air intake covers. Despite irregular construction, improvement is evident. It was the language of bureaucracy acknowledging the obvious. Behind the numbers, something else had shifted. For the first time since the landings in North Africa, crews trusted their machines again. The desert, once the enemy of every bearing and cylinder, was no longer defeating American engines by default. A nameless mechanic's stupid idea had turned into data, and data had turned into policy. The next phase would make it official. Engineers back in the United States were already examining how to turn this improvised cloth into a standardized piece of equipment. Within months, the modification would appear in production models and technical manuals. But in that winter of 1943, the discovery remained what it had always been: an act of observation, necessity, and quiet persistence in the dust. By March 1943, the lessons from Tunisia had begun filtering through every command level of the armored forces. What started as a crude improvisation on the front line was now the subject of formal memoranda moving between ordnance depots and Washington. That field air intake barrier, as it was politely renamed, had become a recognized feature of North African tank warfare. At the Constantine test range, engineers disassembled the modified Shermans for detailed inspection. Cylinder walls once scarred by abrasive dust now showed smooth, metallic sheen. Lubrication systems held their viscosity beyond normal service intervals. Reports compared photographic evidence: 2 manifolds placed side by side, one eroded and pale, the other still coated with a thin film of clean oil. There was no further debate. The cloth worked. By April, the Ordnance Department approved a production redesign. A new intake unit was ordered from the Baldwin Locomotive Works under the title Desert Service Kit. It used the same principle as the field modification, a replaceable oiled fabric pre-filter mounted externally. The official directive made no mention of McCoy or the tank crews who had invented it. It simply described the improvement as a necessary adaptation for sandy and dusty climates. The wording was formal, the recognition absent. But within the technical vocabulary lay quiet acknowledgement that the desert had outsmarted the drawing board. In the field, the difference was immediate. Units entering the final stages of the Tunisian campaign reported sustained mobility even through spring dust storms. Supply columns reached their objectives without the familiar trail of disabled vehicles. Maintenance tents, once filled with engines under repair, began serving other functions. The shift was visible not as ceremony, but as silence, the sound of machines running properly. Captured German records from the same period note the change with surprise. Intelligence reports mention improved endurance of American tanks despite severe dust conditions. Axis crews, once confident that the Sahara itself would wear down their opponents' machines, now faced columns of Shermans that no longer stopped to cool or clean. The adaptation had turned environment into advantage. By mid-year, when the North African campaign drew to a close, more than 10,000 tanks had received some form of the modified intake. Post-war studies by the Army Ground Forces Technical Division later credited the change with extending engine life by a factor of 2.5. In simple arithmetic, the stupid shortcut had saved thousands of engines, countless hours of repair, and an unrecorded number of lives dependent on mobility in open desert combat. Years later, during peacetime evaluations, a single file in the U.S. Army Ordnance Archives preserved the story. Its title, typed in small letters, read Field Adaptations, 2nd Armored Division, North African Theatre, 1943. Inside was the original field note, creased, smudged, and nearly illegible, bearing the penciled sentence that had started it all: "We don't need more filters. We need to keep the air out of the filters." There was no signature beneath the words. The Army had long since standardized the solution, improved it, and forgotten its origin. Yet within that anonymous line remained the entire principle of mechanical survival: observe the problem exactly as it is, and solve it with what you have. The desert had taught its final lesson not through destruction, but through invention born of dust, discipline, and a single moment of clarity at the edge of failure. April 1943. The North African campaign enters its final stage. Supply convoys stretch from Iran to the Tunisian front, and with them travel crates marked Desert Service Kit, Air Intake. Each contains the standardized version of what had once been a strip of tent canvas tied with wire. The new assemblies are machine-stitched, fitted with metal frames, and soaked in mineral oil before shipping. They arrive with a printed tag, installed prior to movement in dusty terrain. At the forward ordnance depots, mechanics unpack the kits under open skies. Each one includes an instruction sheet stamped with the Baldwin Locomotive Works emblem and dated April 12, 1943. The text is concise: 3 steps, 1 illustration, no names. The modification that had begun as an improvised trick by a corporal now carried the full weight of the U.S. Army supply network. In Tibessa, a visiting officer from Washington examines a tank fitted with the new kit. He watches as a mechanic unbolts the intake housing and removes the oiled fabric, dark with collected dust. The engine beneath it is clean. The officer nods, notes the result, and returns to his jeep. No ceremony follows. The success of the idea has made it invisible, an accepted fact of operation. Meanwhile, crews at the front accept the change with the same practical logic that created it. They call the kits factory rags and keep a bundle of spares tied to the turret racks. During halts between movements, drivers replace the saturated filters, wring them out with used oil, and reinstall them in minutes. The desert no longer dictates the pace of mechanical failure. The tanks move, stop, and move again. The dust still rises, but it no longer wins. British maintenance units adopt the same pattern. Reports from the 8th Army workshops at Medjez El Bab confirm parallel results: identical reductions in engine wear, identical improvements in reliability. Allied liaison officers record the adaptation as a shared technical standard between American and British forces. Within weeks, Commonwealth tank units across Egypt and Libya are using the same modification. What began as one mechanic's local solution has become an inter-allied specification. Back in the United States, factories adjust production lines accordingly. By May, the Baldwin and Chrysler plants integrate the Desert Service air intake assemblies into all outgoing Shermans bound for overseas deployment. The language of manufacturing now mirrors the logic of improvisation, a machine improved by the environment that once destroyed it. Internal correspondence within the Ordnance Department reflects a quiet satisfaction. Letters between engineers mention a remarkable case of field innovation. One memorandum, circulated in May 1943, contains a brief acknowledgement: adaptation originated in theatre, subsequently confirmed by controlled test, now standard issue. It is the only official sentence that connects the pre-filter's lineage from field improvisation to institutional approval. In North Africa, the practical effect is visible in the landscape itself. Tank columns crossing the desert no longer leave a trail of disabled vehicles behind them. Recovery trucks sit idle for days. The sound of stalled engines, a constant feature of earlier months, is rare. Dust storms still sweep across the camps, but engines continue to start after they pass. The frontline soldiers never call it innovation. To them, it is just the way things should have been built from the beginning. The modification becomes part of the machine's identity, indistinguishable from its steel or paint. In the quiet evenings after maintenance, the oiled fabric hangs from lines to dry, fluttering in the warm wind. Its movement is small, almost unnoticed, yet it signals the difference between defeat by nature and mastery through observation. By late spring, the desert no longer dictates the rhythm of combat. The tanks, once victims of the sand, now move as though the landscape itself has accepted them. And somewhere in that transformation lies the trace of a mechanic's hand, unrecorded, uncelebrated, but permanently imprinted in the machinery of war. By summer 1943, the North African campaign was over. The last German units had surrendered at Cape Bon, and American armor began preparing for the next phase of the war, the invasion of Sicily. The tanks that rolled onto landing craft in July carried not just new paint and supplies, but the lessons of the desert embedded in their design. Each Sherman bore the improved intake assembly, a standardized echo of a field-born idea. When the first wave landed near Gela, Sicily, the crews noticed something unexpected. The same pre-filters that had protected engines from dust now kept out volcanic ash from Mount Etna's eruptions. The air was thick with fine grit, but the engines held steady. The adaptation that began in sand now proved useful on stone. The Army's technical observers noted it again in post-mission reports: air filtration satisfactory under volcanic conditions. From there, the modification traveled quietly through the logistics chain. Replacement parts shipped from New York to Algiers, from Algiers to Naples, each bearing the new specification. By the end of the year, every M for Sherman produced in the United States included the intake pre-filter as standard equipment, whether destined for desert or temperate climate. No longer an improvisation, it had become doctrine, embedded in steel and paper, accepted without discussion. Back at the Detroit Tank Arsenal, engineers studying return vehicles examined the effect of the change in long-term wear. Their findings were precise: cylinder scoring reduced by 70%, valve failure nearly eliminated, and oil degradation slowed by a measurable margin. The data confirmed what had already been learned through practice, that reliability was not the product of complexity, but of understanding the environment in which a machine lived. For the Ordnance Department, the McCoy modification, as some officers still called it informally, became a case study in adaptive engineering. Training manuals printed in late 1943 carried a section titled Lessons from Desert Operations. Beneath it, a short paragraph summarized the entire event in neutral prose. Field maintenance may reveal environmental factors unanticipated in design. Practical adjustments from experienced personnel should be recorded, tested, and where suitable, incorporated into production. It was a bureaucratic phrasing of a simple truth, that innovation does not always come from laboratories or design offices. Sometimes it comes from observation, from necessity, and from the ability to see failure not as defeat but as information. When American tanks crossed into Italy later that year, ordnance officers continued collecting data. The same intake systems now faced rain, mud, and mountainous terrain. They performed without issue. The cloth pre-filter, originally conceived to stop sand, now trapped moisture and grit equally well. Maintenance intervals extended further still. The stupid shortcut, as McCoy had once called it with self-deprecating humor, had evolved into one of the most effective reliability improvements of the entire Sherman series. Archival footage from the period shows long convoys climbing narrow Italian roads, their engines running evenly, exhaust smooth and unbroken. None of it suggests improvisation or accident. Yet each tank carries within it the memory of a dusty maintenance yard in Tunisia, where a single mechanic looked at a clogged filter and decided to think differently. In later years, U.S. Army engineers would cite the North African experience as the foundation for a new doctrine of field adaptability. The process of observation, modification, and standardization, once informal, became formal procedure. Every future campaign, from Europe to the Pacific, would carry that legacy forward. The desert had not only tested machinery, it had tested the Army's ability to listen to its own mechanics. In that test, quiet ingenuity had prevailed. In 1945, after the war's end in Europe, the Army Ordnance Department began a comprehensive review of all field modifications adopted during combat. The study, compiled under the title Operational Adaptations and Engineering Responses in Mobile Warfare, filled hundreds of pages. Among entries on fuel efficiency, transmission durability, and armor performance, one minor section, barely 2 pages, described the air intake pre-filter modification, M for series. Its language was calm, almost detached. Field-derived method of particulate exclusion demonstrated significant gains in power retention and engine longevity under arid conditions. Recommended for permanent integration. Behind that technical phrasing lay an unspoken recognition: the battlefield had reshaped American engineering practice. The desert had not only tested the limits of machinery, it had forced the Army to bridge the distance between the designer and the mechanic. In a war defined by industrial scale, a single observation made by a corporal in Tunisia had traveled upward through the entire hierarchy until it reached the drafting tables of Detroit. At the Aberdeen Proving Ground, engineers disassembled return tanks to quantify the results. They measured cylinder erosion, inspected filter assemblies, and recorded the precise reduction in particulate intrusion. Their graphs showed that the modified system reduced internal abrasion by 70% and doubled mean engine lifespan under dust exposure. These findings, supported by physical evidence, entered the next generation of vehicle design. The postwar M26 Pershing and early M46 pattern incorporated dual-stage air filtration directly modeled on the North African experience. The process also reshaped doctrine. Technical manuals distributed to maintenance schools in 1946 included a section titled Field Feedback Integration. It directed officers to record local adaptations observed effective under theater conditions and forward technical data to ordnance for evaluation. This procedure, born from necessity, institutionalized the idea that knowledge could move upward as well as downward. In Washington, procurement officers revisited their understanding of reliability. Earlier designs had treated the environment as a constant. After North Africa, the environment became a design parameter. Dust, moisture, temperature, each entered the equations of endurance and maintenance cost. Engineers began to speak not just of performance, but of survivability through context. Among veterans, the memory of the to-filter cloth lingered only as an anecdote. Tank crews who had served in Tunisia recalled tying fabric around engine vents and hearing officers laugh before the results proved otherwise. The story circulated quietly in ordnance circles, a reminder that simplicity could outlast authority. A letter preserved in the Ordnance Archives, written in 1947 by Lieutenant Colonel Frank Balcombe to a colleague, captures that tone. It's worth remembering, he wrote, that the desert solved more engineering problems than we did. We just learned to take notes. In the broader post-war context, the modifications legacy extended beyond tanks. When U.S. manufacturers designed heavy machinery for construction and mining in the late 1940s, they used filtration systems derived directly from the Army's wartime experience. Civilian patents referencing multistage air induction and cloth prefiltration trace their lineage to that same moment in Tunisia. What began as an emergency repair had become a principle of modern engine design. By the early 1950s, when the US entered the Korean War, every armored vehicle deployed carried an evolved version of the desert intake, smaller, more efficient, but unmistakably descended from the same logic. None of the official documents mentioned its origin. The name McCoy never appeared. Yet the design's endurance made the anonymity irrelevant. The desert's lesson had outlived its geography. Through data, design, and doctrine, it had embedded itself in the machinery of a new era, an era where every field mechanic carried, perhaps unknowingly, the inheritance of that stupid shortcut that once kept an army moving across the sand. In the years that followed, few remembered where the idea had begun. The Sherman tank itself became a symbol of industrial victory, produced in tens of thousands, crossing continents and climates. Yet within its story lay a smaller truth: quiet and mechanical, survival often depended not on superior design, but on the capacity to observe what was failing and correct it with what was at hand. The Desert War had exposed a simple paradox. Armies could deploy modern machines across oceans, yet those machines would still bow to wind, dust, and heat unless they learned to adapt. The mechanic's cloth, soaked in oil and tied over a steel vent, became a metaphor for that adaptation, a bridge between engineering theory and the physical world it served. It was not elegant, but it worked. And because it worked, it endured. Post-war reports described the pre-filter in neutral terms, stripped of its human origin. To the archive, it was at field adaptation successfully standardized. To the crews who lived through those months in Tunisia, it was proof that invention required no permission. The solution did not emerge from command orders or laboratory drawings, but from the ground itself, from dust settling on a man's hands as he studied an engine that had once refused to breathe. By the 1950s, the lesson had entered the vocabulary of American engineering without fanfare. Military technical schools taught the principle as feedback integration. Civilian designers called it field-informed reliability. Decades later, when air filtration systems for aircraft, trucks, and agricultural engines were refined, they all carried echoes of that same logic: keep the environment outside, let the machine live within. The North African War faded into history, its victories measured in miles gained and enemy forces defeated. But between those official numbers lay another kind of achievement, less visible, more enduring. It was the moment when observation became invention, when a man looked at failure and decided to adjust reality instead of waiting for permission. In 1973, an Army historian cataloguing ordnance records came across a faded field note from 1943. The paper was brittle, the pencil barely legible. It read, "We don't need more filters. We need to keep the air out of the filters." There was no signature, only the unit designation of the 2nd Armored Division. The historian copied the line into his notes and filed the original under miscellaneous. It would never appear in official histories or commemorations. But within that single sentence lay the entire sequence of wartime innovation, the recognition of failure, the act of improvisation, the discipline of testing, and the humility to let results speak for themselves. It captured the kind of intelligence that history rarely names, not theoretical brilliance, but practical awareness. The desert remained silent now, its rusted hulks half buried in sand. Wind passes through the open grills of forgotten machines, the same way it did 8 decades ago. Somewhere within that sound, faint but continuous, is the echo of a mechanic's idea, an idea born from necessity, proven by observation, and preserved not in monuments or medals, but in every engine that still starts cleanly under dust and heat. No one remembered his name. But the machine did.